Yeah, can you see my screen?
Yes, yes, visible.
Yeah, okay. Uh, yeah, okay. So, welcome to the fourth lecture on randomized algorithms. So today, in the last lecture, we were discussing randomized quicksort, and we uh, left the analysis at some point, and today we'll continue from there. But before that, let's quickly recall what we were doing in randomized quicksort. So it's almost exactly the same as quicksort. The only difference is that instead of in quicksort, we were picking pivot in a deterministic manner. So the pivot would either be the first element or the last element or something like that. In randomized quicksort, we pick the pivot randomly. So let's say the array has n elements. We pick one of the indices randomly, with all indices being okay. So we pick one of the indices uniformly at random. So every index has the same probability of being picked. And then if the index picked is R, ARR becomes our pivot. Okay. And when we recursively call uh, like, and to like and in the recursion we recursively call randomized quicksort instead of quicksort on the two subarrays. So this is the only difference between randomized quicksort and deterministic quicksort. And we saw so we had started the running time analysis, and we saw that okay, so we argued that since the number of comparisons is what dominates the cost, it's enough to show that the number of comparisons is order n log n. And then we uh, showed that, okay, to show that the expected number of comparisons is order n log n, it is enough to show that this sum is order n log n. And over here, xij takes value 1 if ai and aj are compared and takes value 0 otherwise, right? So the sum of xij's is the number of comparisons. And so if you want to show that the expected number of comparisons is order n log n, what you need to do is show that the expected value of the sum of xij is order n log n. Okay, yeah. And then we had constructed this binary tree. So the root of the tree is the pivot. The elements in the left subtree are everything smaller than the pivot. Elements in the right subtree are everything larger than the pivot. And we construct the left subtree and right subtree recursively in the same way. So the elements in the left subtree are elements ARR1 to ARR pivot, ARR PTR minus 1. PTR is the position where the pivot is located. Then when you recursively call randomized quicksort on ARR1 to ARR PTR minus 1, you would again pick up a pivot, right? This pivot would become the root of this subtree, and same for the right subtree. So the subtree is being created in a recursive manner. Okay. And then we defined a pi as the level order traversal of this tree. And we argued that pi is a permutation of A1 to A. So this is what we had done yesterday, right? So do you have any questions about that, or should we move on to what we have?
Yes. So can you explain the meaning of, it is true that the construction of the tree is clear. So can you
Mhm.
explain the meaning of the term the level order traversal, number one, and the explanation of both the observations?
So what was the second thing? Explanation of?
Explanation of the observation one and the observation two, it is clear.
Okay. Okay. So level order traversal means this. So suppose we have a tree, right? So the level order traversal first visits the root, then it visits the left subject, the left child of the root, right child of the root, and then the recurses. So it then visits the left child of the left child of the root, right child of the left child of the root, and so on. So let's say the tree looks something like this. So this is visited first, then second, third, fourth, fifth, sixth, seventh, and so on. So level by level.
Yes, yes.
So is this fine?
Yes, yes, fine. Even yesterday also we discussed that this level order traversal is similar to the BFSC.
Yes. Yeah. And so we argue that pi is a permutation. Pi because, okay, What's okay? So an element when it has been picked as a pivot, right? So an element appears in tree when it has been picked as a pivot, right? Okay. So and since once you have picked an element as a pivot, you only look at the left. So you only look at l- all the elements smaller than it and all the elements greater than it, not itself. When you recurse, that element is not present in either of the arrays on which you recurse. So every element is picked as pivot only once, and so every element appears in the tree T, and therefore in the level order traversal of T at exactly once, right? So that's why pi is a permutation. So is this pi?
So can you explain this thing because it is slightly somehow I don't know, but then this is slightly difficult to understand. So can you explain this thing by drawing a diagram, by drawing a tree that okay, so why will this lead to a permutation?
Okay. So suppose this is your pivot for the first. So suppose this is your tree, right? And let's say the elements are 1, 2, 3, 4, 5, 6, and 7. The level order traversal looks like this is what the level order traversal looks like, but this has nothing to do with. Uh, so this is not the reason why this would be a permutation.
Yes.
So think of how we did it was we picked the pivot, made that the root, then the elements of the left subtree and the right subtree were elements smaller than the pivot and elements larger than the pivot, right?
Yes.
And this construction was happening recursively.
This construction.
Now, if I want to, yeah,
Actually, there is some audio issue from your side because after some time, after after 1 or 2 minutes, your video gets freeze for some
okay,
time. So
okay.
yes. So I could hear only till that point that wherein you said that okay, this is the traversal, and certainly this is not a permutation.
Right. Okay. So what I said was this is the level order traversal.
Yes.
Reason why pi is a permutation is not that hasn't doesn't have anything to do with level order traversal. It has to do with the fact that every element appears in the tree at most once. Is that exactly once?
Yes.
So let's say every element in the tree appeared exactly once. Then no matter in which order you traverse, the traversal that you get would be a permutation of A1 to AN, right?
Yes. Yes. In that sense, yes. No, I understood. Yes, it's right.
Right. So what we need to see is why does everything appear in the tree exactly once, right?
So every element in the tree would appear exactly once because I mean, once an element becomes the pivot element, that element can never appear
Right.
anywhere else in any of the subtree.
Yes. So everything appears in the tree at most once, but everything appears in the tree at least once because at some point it would have to be picked as a pivot because it has to get sorted, right?
Yes, yes,
Yeah. So that's why a pi is a permutation. So is this fine?
yes, yes, absolutely.
Okay. Yeah. So now, okay. So if this is fine, now let's look at observation two. So observation two says that uh, for any ij that j is greater than I, xij is equal to 1 if and only if I or j appears in pi before any other element in ai to aj. And yesterday we argued that this statement means that the first element to be picked as pivot from this set is either ai or aj.
So,
Let me write ai or
in,
aj over here yeah,
mhm,
because pi is permutation of a1 to a. Yeah. So do you have a question about this?
so actually, this observation is not clear that Xij is equal to 1, it means that I
Oh, so
is,
the,
so we are comparing I and j. Uh, Only then the value of Xij is equal to 1. So what does it mean that Ai or Aj appears in the pi, in the traversal before any other element in this set, Ai to Aj.
hmm.
What does it mean? What does it mean? So
So
can
what
you,
was the question?
so question is that actually the meaning of this observation is not clear. I mean, the language-wise, the meaning of this statement is not clear. That okay, if AI or AJ appears in the traversal
Hmm.
or any other element in this set, AI to AJ, what does it mean that AI or AJ will appear? I mean, before any other elements in this set.
Okay. So, as we discussed yesterday, suppose that we are at a point in the recursive calls where no element in AI to AJ has been picked as a pivot yet. Okay.
Uh, Actually, again, I mean, there is some audio issue. I don't know why.
Okay. So
Uh,
let me try to reach it.
yes, so actually, is this possible? If you can speak a bit slow, then probably I could make it out that what did you say? Uh, some sound is not that crystal clear.
Not visible. Okay. Yeah. Okay. Yeah. Okay. So I was saying that suppose that we are at a point in the recursion where we haven't picked any element from AI to AJ as a pivot yet. Okay.
Okay.
Yeah. Then can AI to AJ appear in different subtrees or would they appear in the same subtree?
Okay, okay. So if we have not picked any element in this set as a pivot element, so then it shows that I mean they would belong to one subtree completely. Because if you could have selected one element as a pivot element in this set, then some of the elements might have moved to the left half and some of the
Hmm.
elements might have moved to the right half.
Right. So until I pick some element in this set as a pivot, they would appear together, right?
Yes.
The first element that I picked as pivot from this set, is this fine?
Yeah. So I could hear till the point that okay, so these elements would be there towards, I mean, one side and will come together if we have not picked any element as a pivot element from this set.
Hmm.
And after that, whatever you said was not audible actually.
So because of that reason, this statement means that the first element picked from this set as a pivot is either AI or AJ.
Oh, yes, yes, yes,
Yeah, so that's what this statement means. So what this observing? Yeah,
yes, yes, it's clear.
yeah. Okay, so what this observation is saying is the following: Xij is equal to 1. That is, Xi and Xj are compared if and only if the first element from this set, which is picked as a pivot, is either AI or AJ.
Yes,
So,
yes.
okay, yeah. Okay, so okay, I'll just write this. Same subtree of T. Yeah, so now to prove this direction, yeah. Okay, so Xij equals 1 means that, okay, but Okay, so first let's prove this direction. So if xij equals 1, then by the very definition of xij, ai and aj must have been compared, right?
Yes.
Yeah, but now suppose that AI, xij is equal to 1, but this did not happen. In that case, I must the first look. Let's look at the first time where I picked some element from this set as a pivot, and let's say that this element was an. Okay, say something in between over here. But in that case, ai would be in one subarray, aj would be in the another subarray when I make a recursive call from there, right?
Yes. Yes.
But now they're in different subarrays, so they would never be compared,
Yes.
right? So if I had picked some other element as a pivot, then xij could not have been one, right?
Yes. Yes.
Yeah. So xij equals one means that yeah. So is this fine?
Yes. Yes. Clear.
So this proves one direction. Now for the other direction, this is obvious, right? Because if okay, so let's look at a okay, so let's say that at this set, and this is the first element to be picked as pivot from this set. So till now, no element was picked as a pivot, and so this entire thing appears in one subarray.
Yes.
Okay. Now if I pick AI as a pivot, it would obviously be compared with AJ because pivot is compared with everything. And if
Yes.
I pick AJ as pivot, it would have been compared with AI, right?
Yes. Yes.
Yeah. So the second that this is obvious because yeah, so this proves the observation, right?
Yes.
Yeah. Okay. So recall that we were interested in the expected value of the sum of xij's, and we have shown that these two events. Okay. Actually, let me go over here and write one more step. So actually, I can simplify this further. So what can I write in a place of expected value of xij? Recall that xij is a 0, 1 random variable.
Yes. So yeah, xij is a random variable. So then we'll have to see the probability of AI and AJ. And what is the probability that AI and AJ are going to be compared?
Yeah,
Right.
so okay, my claim is it's this.
Yes. 0 into probability that xi and then plus.
So this is just this, right?
Yes.
In particular, this statement is true for any 0, 1 random variable, right?
Yes.
Yeah, its expectation is just the same as the probability of the random variable being 1.
Right. Yes.
Yeah, can find if I find this number. Now, whatever I shown over here, and this event are exactly the same. Like they are different only, right?
Yes. Yes.
So the probability of this event is the same as the probability of this.
Right. Right.
Right. So now what I'll do is this event is AI or AJ appears in pi before any other element in the set. Complement is AL appears in uh, pi before any other element in A one AI to AJ, where L is strictly between J, I, and J. Right.
Yes. Uh, yes.
Okay. This is what.
But then why should this be true that whichever L we select, uh, uh, so this thing, I mean, this is assumption or what? Except the first
This
and
is
the last.
observation.
This is observation. Okay.
AL appears in pi before any other element in AI to AJ is the same for all L.
Mhm. Mhm. Uh, yes. Yes.
Because why is this
And
true? This is because of something we are doing in the algorithm.
okay, so will this be true for this statement also, that the probability that AL appears in pi after any other elements in this set would also be true for all the values of the L?
To be the same. But this is much easier to prove.
Ah, yeah.
Okay, so AL appears in pi. Okay, so this it's fine, right? We have seen this. Am I audible?
Yes, yes, you are audible, but then where did we see this thing?
Yeah.
Now this AL is
Huh?
different from AI and AJ. So if AL appears in the
It's not
travel,
right. So whenever okay, so AI or AG appeared in the traversal before any other element, if and only if they were picked as pivots, the same is true for AL, right? So okay, until the point where you pick any element from this set as a pivot, these appear in the same subtree, right?
yes, yes,
But the moment you pick some element over here as a pivot, that becomes the root of a subtree, and
mhm,
the left and right subtrees contain like elements less than it and elements more than it, right? So in the
yes,
level order traversal, the first thing to be picked as pivot would appear first.
yes, yes,
So this is the same for everything in AI to AJ, right? In the set.
yes, yes,
Yeah. So AL appears first if and only if AL is picked as a pivot from this, right? But
yes,
we are picking pivots uniformly at random.
yes.
So the probability of any element being picked as pivot from AI to AJ is exactly the same.
Right, right.
Right. Okay, so now the claim. So because of this observation, probability that I or J appears in pi before any I plus 1. Why? Because each and every L has the same probability, and that probability would, what would that probability be? Sum of all the probabilities has to be 1. So that probability would be 1 over J minus I plus 1, right? I have these many choices. I am picking one from it. It's 1 over J minus I plus 1, right? For one element.
Yes.
So for two elements, I or J, by like these events are, they have no intersection. So their union would be just their sum.
Right. Right.
Because it cannot happen that the event I was picked, AI was picked as a pivot first and AJ was picked as a pivot first. That doesn't make sense, right? Either AI was picked or AJ was picked. Both can't be picked together as first together, right?
Yes. Actually,
Yeah.
yeah, this that thing seems to be clear. The only thing is that when you write, I mean, most of the observations when you write that this thing would appear before any other element in this set.
Hmm.
Actually, it is not making sense probably to me. So, I mean, language-wise, I mean, this the meaning of this term is not clear actually. That AI and
Okay.
AI
So,
appears in pi before any other element. What does it mean actually?
okay, what is pi?
What is
What is pi?
pi? Pi is a traversal, level-wise
Right.
traversal.
Right. So pi is just a sequence of, it's just a sequence of elements of the form A1, A2, AC, and so on, right? So pi
Yeah.
is just a permutation of A1 to AN. So pi just looks like AI1, AI2, AI3, and so on, right?
Yes, so pi would
It's
appear
a
like
list.
one, not starting from AI. Pi would appear as A1 until AN or any permutation of the set A1 to AN.
Right. So pi is any permutation of set A1 to AN. So it's just a sequence of AIs, right?
Sequence of AIs, right? Yes.
Right. And so when I say that AI or AG appears in pi before any other element, all I mean is that this is a sequence. In that sequence, AI or AJ appears before any other element in this set. So let's say the set, let's say I was 1, J was 4. Then what I'm saying is A1 or A4 appears before the other three elements. So it either looks like A1.
Yes, so A1 and A4 will appear in pi before any element in which set A1, A2, A3, and A4.
Hmm.
So what does it mean? I mean, language-wise, what does it mean? I mean, what message you want to convey? That is not getting
Okay,
clear.
so okay, so what does it mean when I say was selected before person B, person C, or person D?
Uh, Actually, there
So
was a
let's say you
pause.
have four people, A, B, C, D. What
Yes.
does it mean? Let's say that person A was, let's say, interviewed before any other person in this set A, B, C, D.
Okay. So A was interviewed before any person in the set A, B, C, D means
Any
that
other person.
any other person, right? So it
Yeah,
means
because
that
A
A
cannot be interviewed before themselves, right?
cannot be.
So saying that A was interviewed before any other person in the set ABCD is wrong because A is also present in ABCD and A obviously cannot be interviewed before they are interviewed, right? So A cannot be interviewed before themselves.
Yes. Yes. Again, there
Okay,
is a
so
pause. Again, there was a pause in the video. So whatever you just now you said, can you write it down here in this? Because after every one
okay,
minute or 2 minutes, your video gets freezed. So something
okay,
is missing in Verdeen, and which is actually, I mean, because of that, I'm unable to understand the proof.
okay. So what I'm saying is interviewed before themselves, right? So what I'm saying is this is false.
Yes, because A is a part of the set.
Right. So this is required.
So A interviewed before any other person in the set. So it means that A would appear first.
Right. And then B, C, D would appear in some order, right?
Yes, yes.
Okay. So now there is another statement. What does this mean?
So this means that B would be interviewed and then remaining elements A to A, C, and D can appear in any order.
Okay. And when I put an or between these two sentences, what does it mean?
So it means that either A will appear first and remaining elements may appear in any order, or B will appear first and then the remaining elements will appear in any order.
Right. So then I can write this or of statements as A or B. This I can do, right?
Yes, yes, yes.
And that's exactly what's happening over here, right?
Okay. So so you should have written here AI or AJ appears in pi. Uh,
Hmm.
yes, yes. AI or AJ appears in pi before any other elements in this set is what is this thing. So and this probability, because now either AI or AJ are the distinct element, and for all other elements, yes, this probability is same. So
Right.
AI or AJ appears, yes. So how can this probability be then? So we are not uniformly picking up the elements AI or AJ. For AI and AJs, I mean things are fixed that either the AI will appear first and then remaining elements can appear in any order, or AJ is
Hmm.
fixed and then remaining elements can appear in any order. So I mean, how can this value be 2 divided by j minus I plus 1, and j minus I plus 1 is a complete interval wherein I am picking any one
Right.
value random. I mean within this interval.
Yes. Okay. So first of all, when I say that AI or AJ appears before any other element in this set, I'm saying that I have, okay, what are the events I'm looking at? I have taken some pivot from this set. What's the probability that it's AI or AJ, right?
Yes, yes.
Okay. Now, what is the probability that that it is AI?
Oh, oh, I see. Yes, yes. So, so the probability of, I mean, picking this element AI is, yes, yes, 1 by j minus I plus 1, and the probability of having either AI or AJ as the element is the twice of it. So it makes sense
Right.
now.
Because these events are mutually exclusive, right?
Yes. Thanks, thanks. It is clear to me
Yes.
now. There
Yeah.
was some issue in the
Okay.
wordings actually.
Okay. So this probability is fine, right?
Yes, yes, yes.
Yeah. So then we saw that expected running time is the sum, and this probability is exactly this, right?
Yes.
Okay. So now we need to simplify this. So mm, for a fixed I, this goes from uh, so if I fix an I, then this would go from j equals I plus 1. So if I put I plus 1, I would get 2, then 3, and all the way up to n. So ah, okay, let me do it like this. Let me change the sums like uh, So I want to set k to be j minus I plus 1, and then okay, so here's one way to do it. So let me fix an I over here. And then j would be at least one more than I, right? So this would start from 2 and go all the way up to n minus I plus 1, right?
Yes.
Is this fine?
Yes, yes. So, yes,
Yeah.
this j
So I
minus I,
can write.
if you fix the value of I, so then this will
Hmm.
become, so this will become what? So if you fix the value of I is equal to 1, then this will be 2 by I plus 2 by I plus 1, and then so on.
No, it would be 2. No, no. So, okay. J starts from I plus 1.
Yes.
So this would start at 2 and go on till n minus I plus 1, right? Because the maximum value of j is n.
Right, right. Yes, yes,
Yes,
yes.
I can write the sum as k equals 2 to n minus I plus 1, 2 over k, right?
Yes.
Okay. And okay. So this is sum over, yeah, because all I'm doing by lowering the index from 2 to 1 is just increase, like adding something over here, right? So this can
Mhm.
quantity. So, okay, 1 plus 1 over 2 plus 1 over 3 plus up to 1 over k is called the kth harmonic number hk.
Yes.
Okay. So is at most uh, 2 times, okay, uh, a, yeah, from h1 to h2. So yeah, this is right.
Yes. Yes.
This is 1, h2 is 1 plus, this is an increasing sequence. So I can just say that this is less than or equals to upper bound every harmonic number by the last one.
Right, right.
Yeah. Okay, so now all we need to do is see how large Hn is, right?
Yes.
Okay, so now what we'll do is we'll prove that Hn is at most log n plus 1.
Mhm. Mhm.
Okay, and this proof would be slightly different than all the proofs we have seen or we would see in this course. So let me draw a graph. Uh, I need more space. So yeah, over here I'll have n. Over here I'll have Hn. Ah, ah, didn't move it properly. Yeah. Okay. I want the axis to align with the grid points. Yeah, now it's fine. Scale. Okay. So let me plot n versus 1 over n, right? So for 1, this is 1. For 2, this is half. For 3, this would be one third, and so on, right?
Yes.
Okay, and now what am I interested in? For Hn, I'm interested in the sum of these values.
Yes. So I have a small point here.
Hmm.
So since this is a summation of say 1 by n, so can we view it as the integration of the 1 by x kind of the thing and
Yeah,
then
that's exactly what they're going to do, but we need to pick the limits right.
okay.
Yeah, okay, so this is the sum we are interested in, right?
Yes.
Now, my claim is this sum is the same as this area. Why? Because this is 1 over n times 1, 1 over 2 times 1, 1 over 3 times 1, 1 over 4 times 1, and so on, right? This area is 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and so on, right?
Yes. Yes.
Okay, so Hn is right.
Yes.
Okay. Uh, Now, what is um, so log 1 is 0. Oh, wait. I did. Okay, I did not draw the bars properly. I want other bars of a different form. Okay, so let me draw the bars like this. Hmm, Vector, merge vector. Why is this getting crooked? Oh no, okay, let me draw that point later. That yes. Uh, No, no, wait. 1/3 wasn't here. 1/3 was somewhere else. Okay, so this is 1/3. Yeah. Okay, why is this that? Yeah, so this was 1/2, this was 1/3, this was 1/4, right? So instead of drawing the bars on the left and now drawing them on the right, it will be clear why. Okay, so again, so hello,
Yes, yes.
yeah, this is 1 times 1/2, 1 times 1/3, 1 times 1/4, and so on, right?
Yes, yes.
So this area, yeah, I have drawn 1/n. Now what I'll do is, you were saying something?
No, no.
Okay, so I have n. Now what I want, oh wait, no, those bars were correct. Okay, the previous bars were correct. I have a better idea. I'm not drawing the bars again. Okay, yes, no. One way I can shift and then move. Yeah. Okay, yeah. So now what I want to do is, okay, so now what's log 1? So log 1 is 0, right?
Yes.
Or okay, rather let me do it like this. Uh, so I have these bars. Now let me, I am not going to get the curve right. Okay, yeah, think of this green curve, right?
Yes.
So the green curve is this, and that plus 1 is up is an upper bound on the area under the blue curve, blue bars, right?
Right.
Yes. Okay. So is less than or equals to. Okay.
Yes.
So now all you want to do is find the area under the green curve. So the green curve is this is the green curve, right?
Yes. Yes.
Okay, not this.
I
From
was thinking of if n is equal to 1 upon n plus 1 and yn by n and not n plus 1. Uh, Fn. No, it's okay. It's okay. It is Fn is equal to 1 by n. It's n varies from 1 to n. It's okay. It's okay.
right. Yeah. So and this is log n equals to 1. Okay, okay, not infinity. So I'm only interested in Hn, right?
Yes.
So yeah, um, too
1 by
many. Okay, so let me call this curve f of x, where n x goes from 1 to n because I'm interested in Hn, right?
yes.
Yeah, and this is 1 over x dx, and this is log x. X is 1 to x is n, right? And this is
Yes.
just log n minus 0.
Yes.
Yeah, so the area under the green curve is log n, and Hn is is upper bounded by that plus 1. So Hn is upper bounded by log n plus 1, right?
Yes. Yes.
Yeah. So therefore, okay, what was your x better than that? 2 times n times log.
Right.
Yeah, and like a comment about this. So like this is not something that will only work in this case. This can work in a lot of cases when you have some function, let's say f of x, and you want to find sum over I in 1 to n f of x. You can upper bound that by an appropriate integral.
Yes. Yes. Yes.
Yeah. So for example, this would have also worked for 1 over n squared, for instance.
Yes. Yes.
Yeah. So like discrete sums can be like upper bounded and lower bounded by integrals, which are continuous sums, right?
Yes.
Okay. So in this case, I was able to upper bound hn by log n plus 1 using an integral. Okay.
Mm.
Now, suppose I also wanted to derive a lower bound on hn. Could I do that using an integral?
So, I mean, for the lower bound, integration should not be used.
It can be used. Okay, so let me show you. Okay, I'll have to draw the bars again. Okay, I'm not drawing the axis, just the bars. bar on the right, I'll have to use the axis.
So if I want to have the lower bound through this integration, then I'll have to reduce the bin size. I have to make the green curve as close as the original area possible.
Oh, no, 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 no. This exactly the same thing would work. So, okay, let me do it and then I'll show you the only difference. Okay, so now if I were, okay, so what is this? This is one. So, ah, okay, so over here I was drawing bars to the left, right, in the first part for upper bounding.
Yes.
So the bar corresponding bar of height 1 was between 0 and 1. Now the bar of height 1 is between 1 and 2. This is the only difference between the two figures. Now if I were to draw the curve for 1 over n, it would look like this.
Great.
Huh?
I mean, such a such a surprisingly simple, strategy is this.
So can you repeat? I did not hear you properly.
No, no, I said that this strategy is pretty useful, pretty good, but then such a surprise. This is surprise strategy. I mean, such a small change, and then we can find the lower bound as well.
Actually, it's not surprising because if you look at the definition of integral, so the way we define it is using like finite intervals, right? And those intervals go to 0.
Yes, yes.
And over there, we do the same thing, right? We have a bunch of integral. We have a bunch, and in one in one case, we draw the bar so that the area is lower and say that these two bars come together, right?
Mhm.
So that's how you define integrals. So if you go back and look at the definition of integrals and draw it pictorially, this is what's happening.
Yes, yes.
So you once used like these can argue that as you keep on reducing the width of these the rectangles with larger area and the ones with smaller area, they start coinciding, and when the value at which they coincide is exactly the area, and that's the integral.
Yes.
Yeah, so it's not surprising that yeah. So is this fine?
Uh, yes, yes.
Yeah. So again, like in this case, it would be HN is mm, X. Yeah, so HN is between log n and log n plus 1.
Yes.
Yeah, this is a tight bound on HN.
Right.
Yeah. Okay, so that was all for lecture 3. We were supposed to start from here today, but we'll do it now. So we have 20 minutes. Okay, maybe I can go over the algorithm. We can look at the proof next week. Okay. Yeah. So, like before that, do you have any questions? Okay, you wrote to me in chat. Okay, yeah. Okay, so okay, I can do one thing. Let me turn off my video, see if that helps. Okay, let's
Yes,
see if this helps. Yeah.
yes, yes.
Okay, so like before we start going to the next topic, do you have any questions about randomized quicksort?
So did you ask me something?
Yeah, okay. So I was saying that before we go to the next topic, do you have any questions about randomized quicksort?
No, 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 it is very much clear to me. Yeah, I understood the
Yeah,
entire proof. My only question is that for the deterministic quicksort also, we do have the average case complexity as of the order of n log n only. And in the randomized
right.
version also, we are getting the same complexity. So why to, I mean, prefer the randomized version of the quicksort over the traditional one?
Okay, so in the tradition, okay, first of all, what we proved in the randomized case was also an average complexity bound, right? Because
Yes,
so what did we show? We showed that the expected running time is at most order n log n, right?
yes,
But expectation is a sort of an average. So we saw that the average running time is order n log n. But over here, what are we averaging over? The input is fixed. The average is over the random choices of the algorithm, right?
yes, 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 yes.
And when you are talking about the average case complexity of quicksort, what are you averaging over?
Over the different inputs.
Right. So both are average case complexity bounds, but the thing that you're taking average over is different. So over there, the average is over the inputs. Over here, the average is over the random choices. So over there, your hope was that you would get a good enough input. Over here, your hope is that you would pick a good enough random string.
Yes, yes, yes,
Yeah.
yes.
So and this is true for randomized algorithms in general, right? So, okay, look at how we define randomized algorithms. The input is fixed. The algorithm samples random strings and then executes on the input, right?
Yes, yes, yes.
But there is another way to introduce randomness, and it's the following. The algorithm does not pick any random strings, but the input itself is picked randomly. So for if you want in the sorting example, the input itself is let's say a random permutation of the array, the elements you want to sort,
Yes.
right? And this is another notion of average case complexity. So this is okay. This is one notion of average case complexity, which is what you usually see in the algo code, right?
Yes, yes.
Yeah, and there is also an area of complexity theory which studies this sort of problems. Yeah. So basically, both these notions are valid notions of average case complexity. But yeah, the one which gets called average case complexity is when you average over the inputs. Over here, you call it expected running time. So is this fine? Is the distinction fine?
Yes, yes, and this is clear to me, and I found this difference so very interesting. So, would it be possible
Yeah.
for you to write this difference in your lecture notes as well? Because I'm going to preserve these notes, I mean, for the future reference. So, yeah.
Okay, so uh, I can do it now. Okay, but okay, so here's what I was thinking. So looking at the pace we are going, we are almost one lecture behind. I don't think I would be able to cover Markov chains in in the last lecture, lecture 6. Okay.
Yes.
So in that case, what I was planning to do is talk about this other notion of average case, this other notion of randomness, where the input is random. With that, I
Yes.
can do in half an hour.
Yes.
So what I was thinking is okay, there is this area of complexity theory called average case complexity, where you assume that the input itself is random.
Okay.
So what I was thinking is maybe I can like talk about that in half an hour.
Sure, sure, sure.
So that's one thing I can do, or I can just write it, let's say, over here at the end of lecture 3 notes. So what is it that you want me to do?
Okay, so you can write these two lines, I mean, after the end of the lecture three. And
Okay,
yes, point. Yeah. So because the difference is so very crucial, and I won't find this
Okay,
difference
yeah.
in many places.
Okay, so okay, I can just say average case complexity is when you pick the inputs randomly, and expected running time is when the input is fixed, but the randomness is in the algorithm, right? So I'll just write
Yes.
this much.
Yes. Yes. Yes.
Yeah. Okay. Okay. So now we have 15 minutes. So let me go over the definition of the problem, and if possible, let's look at the algorithm, and then we'll prove all the guarantees next. Okay. Yeah. So the problem that okay. So the next thing that we'll look at is Kargar's randomized algorithm for min cut, and this is one of the first this is one of the first randomized algorithms, and this actually shows the power of randomized algorithms. Because for the problem min cut, we actually know an efficient deterministic algorithm, but that algorithm is complicated. And when I actually write down Kargar's algorithm, it's like just 3 or 4 lines. It's very simple. Yeah. So this algorithm it actually showed the power of randomization. But before we go to the algorithm, we need to know what a cut is, what a min cut is, and what the problem is. Okay. So let me start by defining a cut in a graph. So let G, yeah, you were saying something?
No. No. No.
Yeah. Yeah. So let G be a graph and V1 and V2 be a partition of V. By this notation, I mean disjoint union. So V is the disjoint union of V1 and V2. This means that V is the union of V1 and V2, and furthermore, V1 and V2 are disjoint. Okay. So
Yes.
let uh, V1 and V2 be a partition of V, that is V is the disjoint union of V1 and V2. Then the cut of V1 and V2 is defined to be all the edges E, such that one of the vertices is in V1 and the other is in V2. Okay. So is the definition of cut clear?
Yes. Yes.
Yeah. So for example, if this were my V1 and this were my V2, all the edges going from V1 to V2 would be in the cut, but all the edges going from V1 to V1 or V2 to V2 would not be in the cut. Okay.
Yes. Yes.
Yeah. And the edges in this set are called the cut edges. The set is called a cut.
Yes.
Okay. So now let me define the problem of min cut. So given a graph G equals V comma E, we want to find a cut with a minimum cardinality. And the cut with the minimum cardinality is called the min cut. Okay. So the problem of min cut is just to find a min cut in the graph.
So does this
So is
mean
this
that,
fine?
yeah, does this mean that
Yeah.
out of the many edges which are crossing the cut, so we have to
Mhm.
find that cut wherein the number of the edges which are crossing the cut is minimum.
Yes.
Okay. Okay.
Yeah. And yeah, before that, like this is called, so like this set is called a cut, and the edges are called cut edges because if I that is cut these edges, the graph would become disconnected.
Yes. Yes.
Because now there is no way of going from V1 to V2, right?
Yes. Yes.
Yeah. And what we are, so what the min cut problem asks is the following. So this is one way to look at it. What is the minimum number of edges I need to disconnect to make the graph? Okay, what is the minimum number of edges I need to remove to make the graph disconnect?
Yes. But then are we talking about the directed graph or the indirected one here?
Okay, undirected.
Okay. All right.
Yeah. And if the graph were already disconnected, then the minimum cut would be zero, right? Because there
Yes.
is a vertex which is not connected to other vertices, let's say. Okay, or rather, let me do it like this. Let's say there are two connected components, C1 and C2 in the graph. There is no edge going between C1 and C2, right? So I
Yes.
can put C1 over here, C2 over here, and the set is empty. So the cardinality of the min cut is zero.
Yes. Yes.
Yeah. And okay, so for Kargil's algorithm, we would need two essential notions. And what we'll do today is yeah. So what we'll do today is we'll look at these notions and the algorithm. Okay.
Okay.
Yeah, so the first thing that we need is the notion of a multigraph. So a multigraph is a generalization of a graph. Okay. So G is equal to V comma E is said to be a multigraph if E is a multiset. So now what is a multiset? Uh,
So if we have the multiple number of the edges within a same set of the vertices, so then
yeah, yeah,
yeah.
yeah. So for example, let's say you have two edge vertices, one and two. In a graph, you would have only one edge between them. In multi-graph, multiple edges are allowed.
Yes, and this includes self loop as well.
Yeah, so this includes self loops, but we like okay, so when we actually use multi-graphs in the algorithm, we would remove self loops. So
Okay.
let's not worry about self loops now. So actually, what we would end up using are called simple multi-graphs without self loops.
Okay.
Yeah, but yeah, we don't need to go into the distinction because yeah, we'll remove loops explicitly in our algorithm, so that's fine. Okay, so if the notion of multigraphs is clear, we can look at the notion of something. Uh, okay, if you look at a notion called contraction and something, sometimes it's also called the contraction operation. Okay, so for a multigraph G equals V comma E and any edge E equals U comma V, uh, we define the contraction of G with respect to E as a new multigraph G prime whose vertex set is V prime and edge set is E prime, where V prime is obtained from V by removing U and V, but adding UV, adding the set UV, I should write, because union.
Yes, yes. It is clear from the diagram also.
Yeah, so basically, okay, pictorially, you can think of this as taking U, taking V, merging them.
Yes.
And now, okay, this definition is important. So E prime is obtained from E by removing all the edges with one endpoint as U or V. Okay, because okay, I've removed U and V from the vertex set. So all the edges connected to U or V have to be removed, right?
Yes. Yes.
Okay. But we would then add edges of the form UV comma W, where WV or WU was in E and W is in V prime. That
So this
is,
is
so I have this new, yeah,
this is not that clear. The union part of the modified set of the edges is not.
okay, yeah, yeah. So, okay, I removed these edges, vertices U and V, but I added a new vertex UV, right? So now what I'm doing is, suppose there was an edge between U and W or V and W, right? Then I'm adding an edge between W and this new vertex UV.
Mhm.
But I'm only doing this if W is in V prime. Because
Yes.
what does that mean? That means that, okay, suppose over here W was U, right?
Mhm.
Then I would have to add an edge between UV and U, but U doesn't even exist.
Mhm.
Yeah, so all I'm saying is the following. Uh, Look at U, look at V, look at all the edges going out of U, look at all the edges going out of V. When you merge them to create a new vertex UV, the edges that were from W to U now would be from W to V, and the edges that were from W to V now would be from W to UV, right?
Yes. Yes.
Yeah. Okay. Just a second. I think I missed something. UV, WV, or WU. Okay, yeah. Okay, right. Okay, so suppose that the original multigraph had no self loops. Okay, and my claim is that even after contraction, you won't have self loops. Why? Because okay, when would you have a self loop between UV and UV if W is UV, right? But this
Mm.
edge is not even present in U.
Yes, yes,
Yeah. So the contraction, so if you started off with a simple multigraph, the contraction operation would still give you a simple multigraph. So yeah, that's why we don't need to worry about self loops.
yes.
Yeah.
So my question is that why can't we merge 1, 2, and 3, 4? I mean,
Okay. So this is okay. So this is just an example. So where I wanted to just show that okay, if I merge one, two, how would the edges change? And over here you can also merge one, two, three, four, but then you would have just one, two, three, four, right? Without
yes, sir,
any edges.
without any.
Yeah.
Yes,
So this was just to illustrate the contraction operation. So is the contraction operation fine?
yes.
Okay, yeah, there is a mistake where it should be contract edge three, four. Yeah. Okay, so now if this operation is fine, let's look at Kargar's Minkert algorithm. And the algorithm is just four steps. So the input is a graph G equals V comma I. So you could also do this for multigraphs, but okay, I'll assume that the input graph is a simple graph. Okay, because most of the times you are only interested in Minkerts for simple graphs. So is this fine?
Yes, yes.
Yeah, and you want to and what you want to output is a and what we are going to do is while G has at least two more than two vertices, we'll pick an edge uniformly at random from the edge set and set G to be the contraction of G with respect to that edge, right?
Yes.
So when would this loop end?
Okay, so when we have two vertices, then this loop will terminate. When we have
Right. And
two,
when you have two vertices, the graph would look something like this, right? Two vertices, multiple edges between them.
yes,
And you would report all of these edges as the min cut. So I'm saying that return E as the min cut. But when you have only two vertices left, all the edges going between them, that's exactly the set E for this graph, right? What is
ye-
multi-graph?
yes, yes.
Yeah. So what the algorithm is saying is just this.
But then,
More than two vertices. Yeah.
but then, how to ensure that what I mean, whichever edges we are getting in between those two vertices would result into a min cut, and we cannot do better than that because we are picking the edges randomly.
Yeah. Okay. So I'll talk about that. But okay, before that, let me just give you a quick description of the algorithm. The algorithm is saying as long as there are at least three vertices, pick an edge at random, contract it, keep on doing this till you get exactly two vertices, and then report all the edges that you have as the min cut. Okay. Now, before like I move on to running time and what you were asking, when I have only two vertices, the entire edge set is exactly the cut set, right?
Yes,
Yeah. Okay. And about your question, so how do you ensure that if it's clear that what you get is the cut, right?
yes. It is a
Yeah.
cut, but then how to ensure that this is the minimum cut?
Okay. So that is one, two, three, four, five, 6 pages long. So that's the proof that we'll see next time.
Okay,
Yeah.
okay,
So it's not immediately clear why this is the min cut. And in fact, the probability of this being a min cut is very bad. It's 2 over n square, and n is the number of vertices.
okay, okay.
So this is going to be a min cut with a very small probability. But the good thing is that that probability is inverse polynomial.
Okay, okay.
And so we did boosting yesterday, right?
Yes, yes, yes.
So if you go and look at the proof of boosting in both the cases, one-sided error and two-sided error, you would can insert instead of 1/3, if you were to try that with an arbitrary parameter, you would see that as long as you only wanted to repeat k times, you could, as long as you only wanted to repeat polynomially many times, you can only tolerate an inverse poly error,
Yes, yes.
right? So even though the success probability of this algorithm would be 2 over n square, where n is the number of vertices, that is still inverse poly, right?
Yes, yes,
So I can boost that to first a constant and then using Chernoff form to to exponential.
yes. Right, right.
But I can directly use Chernoff form and boost it to exponential. Yeah, so basically the probability would be small, but it's still inverse poly, so we are fine. We can. So is this fine?
Yes, yes,
Yeah.
yes.
So now let's quickly be a 1 minute. Let's quickly look at the running time. Okay, so all that we are doing in this algorithm is a contraction operation, right?
Yes.
And my claim is that every contraction operation can be executed in time order size of V if we are using the adjacency matrix representation of the graph.
Mhm, mhm.
And okay, so I won't tell you why this is the case. Like this is actually one of the questions that we would solve in the problem solving session, but you can try to think about this on your own.
Okay.
And so there are at most size of V minus 1 contraction operations because each contraction reduces the number of vertices by exactly 1, right?
Yes, yes, yes.
Yeah, so there are size of so there so like okay there are roughly any time size of V time. So the running time is order size of V square.
Yes, yes.
But then we would see that okay, so and what we would do next time is that if the size of V is n, then the Kargat's algorithm finds the min cut with probably at least 2 over n square.
Mhm.
And to boost this to a constant, we would need n square repetitions.
Right.
So that so if you want a constant error probability, the running time would be n to the 4. N square from here and n square from the repetitions.
Yes. So I
So it
I
is
have
fine.
this like related question here that can we boost every random algorithm or we can only boost those random algorithms wherein the probability is the inverse proportional or inverse of the polynomial.
Okay, so let us say that the success probability is for some number k. K can be
Yes.
any function of n. Okay, so let's say k is some function of n.
Yes.
Then to do this, to boost this to constant, you would need ordered kn repetitions.
Mhm. Mhm.
And that is why you can only tolerate an inverse poly. So you can only tolerate when k is poly n. Because if k was super polynomial, then the number of repetitions required would be super polynomial. Therefore, the running time would become super polynomial, right?
Yes. 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 No, understood.
Yes. So you can boost any algorithm with any success probability. It's just that you would need more repetitions.
Yes. Yes. Right.
Yeah. There is again just like there was nothing special about 1/3. There is nothing special about inverse poly.
Mhm. Right.
Efficient is poly, right? And that's why you need to cut it off at inverse poly.
Yes.
Yeah. Okay. So is this fine?
Yes. Yes. Absolutely.
Yeah. Okay. So I have also uploaded. Okay. So what I've done is I've put all the notes and videos in a Google Drive folder and uploaded the link to that in the on the course page.
Okay. Okay. So I will
Yeah,
check out
but
the.
the videos are taking too much space on my Google Drive. So what I'm thinking of doing is like creating a YouTube channel for this course and just putting the videos on YouTube and linking it on the page.
Yes. Yes. That would be
Yeah,
great.
so that I'll do today.
Yes. Sure.
Yeah. Okay. So then see you next week. Again, on Friday we'll again meet at peak from 6 to 8, 6 to 7:30.
Yes, yes, yes.
Yeah,
Thank you so very much. Thanks.
yeah,
This session was so very useful. The only thing is what that there was some audio and the video which is
yeah.
except that yeah, this was an interesting session. Thank you so
Yeah.
much. Bye.
Thanks. Bye.